So for those of you watching online, hello, I'm David, coordinator of the Maths Learning Centre, and that's enough of that. I do that so that people know what I look like when they come into the Maths Learning Centre. So everyone knows my voice, but it would be nice if people recognise my face. I don't know anyone, even people who I see every day. I struggle to remember their names, but people can at least know who I am. Okay, so this is the Maths for IT revision lecture. I've been asked to talk about cryptography, and in particular the RSA. So let's see. I warn you now that because Maths for IT is a smaller course than, say, Maths 1B, I don't see as many students. Not to say that people don't struggle with it, but there are just less people. Because in second semester I spent a lot of time at Roseworthy campus and helping people with their statistics, I also don't see as many students. So I haven't had as much chance to learn the stuff that's in Maths for IT. So I can't just, like in Maths 1A, I can't just basically do a quick seminar on anything in the course. So be aware that I am working wholly off the notes and trying to figure out a way of putting it together that makes sense to me. I'm hoping that that's useful to you because that's what you have to do. You have the advantage of having seen the lectures, which I have not. So please, if I say anything that sounds a bit strange, let me know, and I will go to the purity of the notes and check to see what's going on. And if I forget anything, let me know and say, oh, you didn't, could you cover, and let me know, because that's much better for everybody, because then everyone will get things covered that they need. So let's have a look at this. Well, the philosophy of cryptography, as far as I'm aware, is that you have a message which you encrypt, and it's there's a name for this, and then you have an encrypted message, which you send and then your friend at the other end, who is usually called Bob, and this is called Alice, because Alice starts with A and Bob starts with B, and it's going from A to B, decrypts it to produce the original message again. And the idea is that this encryption thing here is the reverse of this decryption process, and so that's the idea. And usually the way that you decrypt things is involving some sort of key. And the metaphor there is that by encrypting a message, you're putting it in a locked box, and then the other person at the other end has to unlock the box to let the message out. That's the metaphor there. And it's not necessarily true that you use the same key to encrypt as you do to decrypt, which is how the RSA works. So there you go. And the simplest ones are ones that do one letter at a time and do something to that letter to produce an encrypted letter, and then that's sent, and then the person at the other end decrypts it one letter at a time. Right. Now, the original message is usually letters, and the encrypted message is sometimes letters, but often numbers. And the process by which you do this encryption and decryption, because this is a maths course, is usually a mathematical process. Like converting all your numbers to your letters to numbers, adding 3 to all of them, and then there'll be new letters based on that. Right. Now here's the thing. There are only 26 letters in the English alphabet. Even if you use both capitals and smalls and all of the punctuation marks, you only get to about 60 different characters. And if each of them is a number, and you do some mathematical process like adding 3 at the end, you'll fall off the numbers that are possibly allowed to represent letters. If you're at the last number, which is maybe 60, and you add 3, you're at 63, there aren't any letters that represent that. And so what you do is you do modular arithmetic, meaning that it wraps around again and you go back to the beginning. Okay, so it's all basically based on modular arithmetic. The RSA algorithm is a little different in that sense. It still uses modular arithmetic, but on a much larger scale than that. So that is what it's all based on, and it's because there's only so many letters to go around, and therefore there's only so many numbers that you can choose from, and your calculations have to fall back inside that same list of numbers. That's my understanding of the general philosophy of mathematical cryptography. Sweet. So, some of them, let me just flick through here and see if I can find a list of all of the different ones that you've seen. So we have some terminologies. I'm just going to list the names and we might come back and talk about them more. But in the notes we've got ciphers, and you were told about, shift ciphers. One of which was Caesar's cipher. So there's some of the things, that's one of the things that we've seen. I might just get my rubber and make that a little prettier. So otherwise forever it will have a... It's not S-H-I-P-H-T. So shift ciphers, we saw them. I'm just making a list. Caesar's cipher was an example of that. Oh, there's the Vignere cipher. The RSA and that appears to be all of the ones that you've been told about. Did they tell you about the Hill cipher? Does that sound familiar to you? No? Okay, cool. Just checking. That's one of the ones I learned when I did cryptography. So the courses have changed since then, so I'm just checking. All right, cool. So you've actually only been given the names of 3 different kinds of cryptography systems. You've been given the name of cipher, shift ciphers. You've been given the name of the Vignere cipher and the name of RSA. And that's actually quite a small list. It seems like a lot more when you look through the notes, but there's only a few different types. And that's the sort of thing that I often do when I look at when I go back and study things is I just make a list of everything that's there. Even if I don't write down what it is yet, I just make a list. At least I know what I'm working with. It's just a bit of a study skill thing. It helps when you're making cheat sheets to do that too. You've got a list of everything that there is. You don't necessarily want to put it all on the cheat sheet, but then again, if you were going to, you wouldn't want to miss anything. So that's how I do it there. Okay, so let's see. I'm just going to write down what they actually are. So now that I've found all of them, let's go back and find what they are. Let's see. A shift cipher you shift the alphabet forward by however many letters. Okay? Cool. And Caesars is when the K is 3. Basically, it's called Caesars because it was referenced in somewhere, okay, as Caesar having used it. So, who knows where. If I was paying more attention, I would probably have known where, but I wasn't, and I could go look it up probably. So somebody at some point said that Julius Caesar used this one, though the letters were slightly different at that time. They didn't have a W at that point, for example, so it wouldn't have been 26 letters. So that's the idea behind it. So you can either just write the alphabet down, and then shift everything over. So if I wanted to encrypt, say, a nice short message. That's my message, and then that will encrypt to, let's see, I'll use Caesar's cipher. So here's N, 1, 2, 3, Q, O, 1, 2, 3, R, W, 1, 2, 3, Z. Yay! And that's the encrypted message. Lovely. And the point being that if you went off the end, you'd come in at the other side. So if I did say yes, the Y would go to 1, 2, 3, B, H, S. Ta-da! And you can use whatever letters you like, whatever shift you like. I'm using Caesar's because it gave me a decent way of doing it. I'm just going to draw one of those. So the Y goes 1, 2, 3. That's what happened to it. Okay, and that's the basic idea of modular arithmetic, actually, is that everything wraps around at the edges. And so this Y will wrap around to here, and this end joins up to this end. And so if I add 3 to here, I end up around here. If I subtract 5 from here, I'll end up over here. That's how modular arithmetic works. It's not really any more mystical than that, really. Other than the fact that you don't have to draw a diagram and wrap things around to do it, you can just get used to the concept that if you just keep subtracting, in this case 26 from things, you can get to the number that you want. So that's the other way of dealing with it. You can label your letters from 0 to 25. You could, if you wanted to, label them from 1 to 26 if you wanted. And this is the 26 counts as 0. And so the other way of doing it is to say, etc. And this is 0, 1, 2, 3, 4, 5, 6, 7, 8. Point out that you could label the letters in whatever way you wanted, okay? You could start at 1 for A and put 0 over at Z, But I have a feeling that when your lecturer does it in the exam, they will probably start at 0 for A. And so just keep that in mind when you're decrypting something that's written as letters, that's written as numbers with a shift cipher, that they're probably using 0 for A, because that's what they told you that they did. And so then the idea would be that now would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 16. 23. And then we add 3 to everything. And we get 18, 19, 26. And 18 is... So if you're going to end up doing this in your exam, just have a quick flick through. And if you do any cryptography, which you will, one of the good things to do would be to, during reading time, write down your alphabet and the numbers that go with them. Because then you won't have to count all the time. You can just look it up. This makes it quicker. Z, Y, X, W, D, U, T, S, R, Q. 26, 25, 24, 23, 22, 21, 20. Did I get my N right? 1, 2, 3. Maybe my N is the wrong letter. Oh, N's only 14, isn't it? Is that right? Oh, crap. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, but I started at 0, didn't I? So everything's wrong. Ah, that would be why. Common trap, eh? Right, that's better. Much better. So it was 13, then we added 3 and it became 16. And O was... and W was 22. So 16 was Q, 17 was R, and 25 was Z. Oh gosh, that would throw me off, because I actually know quite a few of the letters that's starting at 1. I know that I is 9, for example, and O is 16, because they're square. That would throw me off, and so I would actually have to, when I'm studying, write out a list so that I didn't get thrown off by knowing when I start with A as 1. Okay, cool. So that's the shift ciphers, and you can choose whatever shift you like, plus 10, plus 20, minus 3, doesn't matter what it is. Cool. And let's look at the next one. So the Vignere cipher is the one where you do a different shift for each letter in turn. So with an ordinary cipher, you just add 3 to all of them. With the Vignere cipher, you'll add 3 and then add 5 and then add 7 and then add 1 and then you'll 3, 5, 7, 1, 3, 5, 7, 1. So you have a list of different things to add. And that's the key. And it can be any length you like. And that's the idea. So it's a shift, but a different shift for each letter in turn. So for example, I might have K be a list of like something like that, just randomly, maybe a 12. And then I could have a word that's as long as I need it to be and just cycle through the different shifts. That's my message. No way, Jose. Except Jose is with a J, isn't it? Sorry about that. No way, Jose. Because it's Spanish. And so we can turn each of them into a letter, into a number. 13, 14, 22, 0, 24. J would be 9. S would be 18. Then I could successively do that trick there. So 13 plus 1 is 14, 14 minus 1 is 13, 22 plus 12 would be, well, 22 is the same as minus 2, so that would be 10. 0 plus 3 is 3, 24 plus 1 is 25, 9 minus 1 is 8, 14 plus 1 is 50, plus 14 plus 12 would be 26, which is 0 again. So the idea is that it wraps around at 26, you go from 0 to 25, and then when you get to 26 it starts at 0 again. So when I add 12 to that, I get 26, which is 0 again. 18 plus 3 would be 21, and 4 plus 1 again would be 5. And so you just keep cycling through the different shifts so that you can figure things out. And you have to do it as modular arithmetic. So just to point out for this one, to show you what I did to get to my 0 here, 14 plus 12 is 26, which is congruent to 0 mod 26, and that's how we got to this answer here. And just another one for, I did it as a 12 as well, and that was 22 plus 12 is 34. Oh, I think I may have gotten that one wrong. And so if I subtract 26 from 34, I'll get 8. Sorry about that. Tried to be clever. The other way that I did it off the top of my head, which I did wrong, is that 22 is minus 4. It's 4 down from 26, so 22 is minus 4, and minus 4 plus 12 is 8, and so that's a different way of doing it. So whatever way you think is best, modular arithmetic is really quite cool. Any number can be replaced with any other number as long as they're whatever apart, so in this case 26 apart. So 22 can be replaced with minus 4 because I subtract 26 and that's what I get, and then I can add 12, and that's a little easier than adding 12 first and then subtracting 26. Okay, right. I was hoping that if I just did some of this and mentioned how the modular arithmetic was working as we went along, it might make more sense. And then we will look up make the modular arithmetic make more sense. And then we're going to look up these numbers and see what they are. And so 14 was O, 13 was N, 8 would be I, that would be D, that would be Z, that would be I again, O, no, that's a 0, so that would be A, 21 was V, and 5 would be F. All right. Right, so one of the problems, the nice thing about this one is it's way more secure than the shift cipher. If you know someone's using a shift cipher, then there's only 26 shifts to try, and you also know that every letter always goes to the same letter. So all the E's will go to the same letter. And if you count up how many E's there are, because E is like the most common letter by twice as much, basically. It's twice as common as any other letter. well, maybe not twice, maybe 1.5 times, but E is like way more common than any other letter by a long way in English, and so if you count them up you can say, oh, well, there's a whole heap of this letter, that must be E. And if you know it's a shift cipher, you've already figured it out then, because you know how far E is from the letter that it is. Right, but the Vignere cipher is harder because different positions use different shifts. And so an E won't always become, say, a Y. In our case, this E became an F. An E won't always become an F. Sometimes it'll become something else. And so that makes it harder, especially if you don't know how long the list of numbers is. If you knew it was 4 numbers long, then you could just do every 4th letter and go, well, count up all the E's in that bit, as long as the message was long enough. And the thing with cryptography is that when it's used in practice, you're actually encrypting like huge strings of things, usually. So, yeah, if you've got enough of them, you can do that. But if you don't know how long it is, that makes it really hard. Right. So, that's those two. And they're quite straightforward. And then RSA is like way different and harder than all of those. So this is where I'm going to read very carefully. Right, so let's look it up and see what it says. So in the notes there's this thing here, and I'll zoom in on that. We need to get a message from A, who is Alice, to B, it's Bob. Generally, I believe the person who's going to intercept the message in the middle is often called Oscar. O for opponent, but anyway, computer scientist. And just basically anyone working in a field comes up with all sorts of quirky little names for things. Chemistry seems to be boring in that sense, but maths and computer science, people come up with all sorts of very quirky names for all sorts of stuff. And theoretical physics is like that as well. Things that you can physically hold tend to have normal names, but things that you're just imagining, like crypto systems, tend to have little cute stories and names like that to go with them. And that's why in particle physics we have quarks, which are named after a random word in a poem. So, yes. So this says that Alice composes a message and then she encrypts the message. Okay, so no, just a second. Bob generates a public key and a secret key. Alice makes a message of her own, which she wants to send to Bob securely, and so she uses Bob's public key to encrypt the message, and then he uses his own secret key to decrypt the message. That diagram makes very little sense to me. I'm going to redraw that as we go. So let's look at RSA. So let's see. Bob picks 2 secret large prime numbers. So this, I'm just going to write it out as we go, because writing makes more sense to me than just reading. So we've got P and Q, which are secret prime numbers, and then creates N, which is P times Q. Whoops, sorry. I've got to zoom out again. Okay. And then what we do is we create a new number. So we think about the new number P minus 1 times Q minus 1. Yeah. And then choose E co-prime to this. Okay. Good. And then you publish E and N. Sorry, I don't think it really matters, but we publish N and E. Okay, So we're just setting it up now. There's a number n, there's a number e. Secretly, we have created that number n out of two prime numbers, and then we've created a different number, like this number here. It'd be really nice if that number had a name, but a different number. And we grew, so there's like 1, 2, 3, 4, 5 numbers involved here, and 2 of those 5 have been published. Okay, doing well. What happens next? So Alice has a message. So, alright, so this is a bit different. So Alice is still the one who wants to send a message from A to B. But the thing is that Bob is providing the means by which to do this. So Alice wants to send a message from A to B, but Bob is telling Alice how to do that. Okay. So let's see. 3, to encrypt a message, we go, and the messages come in numbers mod n. N is that big P times Q. Alright, so the idea is that m could be anything from 0, 1 up to whatever n is. Okay, that's what this means. And let's see. So message m, and then we encrypt, and we get the encrypted message is m to the e mod n. Okay. That seems important, which is called C apparently. And then Bob decrypts the ciphertext. So we've got encrypted, which is called C, and then the decrypted message is C to the D mod n. Okay, cool. Right, that is how it works. I really feel the need for a picture, so just give me a second. So when we have Alice sending a message to Bob, you have a message M encrypted, and it becomes C, which is equal to M to the D mod N to the E mod, oh crap, M to the E mod N, and then you decrypt it again, I'm going to draw that again. So we have a message encrypted, which is M to the E mod N, and that's called C, and then at the other end that's decrypted, which is C to the D mod N, which is M again, and D, I haven't written down what D is. Okay, where this D, so that's another secret number. Co-prime to this, and D is E to the minus 1 mod P minus 1 Q minus 1. Okay, cool. So it's a number that you multiply by D to get 1 mod P minus 1 Q minus 1. Alright. And then to get all these numbers, the N is P times Q, and the E is co-prime to p minus 1 q minus 1, and the d is e to the minus 1 mod p minus 1 q minus 1. Sweet. I think I understand what's going on here now. There we go. I feel aesthetically pleased by my diagram now. I just had to put some boxes and stuff in. So that's what's going on. Okay, so I have a feeling that in many assignment and exam questions you only have to do half of this process. You have to do the decrypting or the encrypting, or possibly you encrypt something and you decrypt something else. Right. So the security of this is reliant on the fact that we can't figure out what the E is without first figuring out what P minus 1 Q minus 1 is, and we can't figure out what P minus 1 times Q minus 1 is without first figuring out what P and Q are. And we can't figure out what P and Q are without factorizing N. And that's the really hard bit. And so that's the thing that makes this hard. So we need to figure out what the D is. We have to figure out what this is, and to figure out what this is, we need to know what P and Q are, and to figure out what P and Q are, we need to be able to factorize N, and that's the problem. There are some things that you can use to attack it, of course, if the P's and Q's are small. So since you know that E is co-prime to P minus 1, Q minus 1, that's a little bit of extra information. Yeah, because we normally choose P and Q to be super huge prime numbers, that makes the whole thing really difficult. Okay, let's see if we can actually do one. Maybe I'll do one from one of the past exams, hey? What's this under? It's under discrete. Let's see. So you publish n equals 21, e is equal to 5 as your RSA public key. Oh, let me tell you what year this is. That's 2011. Your friend uses this to encipher, or if you like, a message to you containing a single word, the ciphertext of which is this. Decipher the message to find the word, showing all your working. Okay. So the point here, oh look, they've helpfully provided the list of letters and what numbers they go with. Oh, but look, there's one. A starts at 1. Okay, sorry about that. That's super confusing to me. Check what your lecturer said this year, because as far as I can tell, different lecturers have different expectations as to whether it starts at 1 or 0. I'd be happy here. See, look at this. Yeah, I is 9. That's right, the only one. Oh, isn't 16, it's 15. Oh well. Anyway, sorry about that. Oh look, I and Y make the same sound sometimes, and they're both square. Sorry. Anyway, so we're going to, in order to do this, we need to find what the secret key is. Okay, because according to our picture, let me just write this out again. We have that E is 5 and N is 21. Okay, so looking at this, the N here is 21, which is really P times Q for some P and Q, and the D and E are inverses of each other, mod P minus 1, Q minus 1. So we have that D is E inverse. So if you really did have a public key crypto system, you personally would know what E was, but they're telling us to figure it out. And the reason they're doing that is so that we can prove to them that we know what the secret, how this system works. Okay. And so this is the secret key. Okay, and so we're going to need to factorize n. So 21 is 3 times 7. And they are the only prime numbers that go into 21, so sweet, we've factorized it. I can make p and q whichever one of those I like. And so therefore my number p minus 1, q minus 1 is 2 times 6, which is 12. So I've got 3 minus 1, which is 2, and 7 minus 1, which is 6, and that's 12. Okay, so we're nearly there. Now all we need to do is figure out what d is. So d is 5 inverse mod 12. So that means it's the number that I multiply by 5 to get 1 mod 12. That is okay, because the idea is if I times both sides by 5, I get 5d equals 1. Okay, so I just need to try and figure out what number I multiply by 5 to get 1 mod 12. If I wanted to, I could use the Euclidean algorithm to do that. Alternatively, I could just keep multiplying 5 by stuff until I got something that made sense to me, which is what I would probably do since 12 is quite a small number. So let's see. 5, 10 is congruent to minus 2 times 5 again. So what I'm doing here is I'm continually adding 5 because I want to multiply by 5. So this is 1 times 5, this is 2 times 5. If I add another 5 to the minus 2, I'll get 3. Looks like I'm going to have to go quite a long way. So if I add another 5 to the 3, I'll get an 8. Add another 5 to the 8, I'll get a 13, which is congruent to 1. Excellent. 5 is its own inverse, mod 12. So the idea here is I'm saying, you know how multiplication, when you first learned it as a child, you did it as repeated addition. So we have 1 times 5 is 5. Add another 5 to get 10, which is the same as minus 2. Add another 5 to get, and that gives me 3. Add another 5 gives me 8. Add another 5 gives me 13, and 13 is back to 1 again, which is my hope. So I have here that 5 times 5 is congruent to 1 mod 12, and this number here is my d. So therefore d is 5. So just to write down exactly what I did here, I did repeated addition to find the multiples of 5. That's what I did there. Okay, so now I know what D is. So therefore, to decrypt C, we do C to the D mod P minus 1 Q minus 1, i.e. C to the 5 mod 12. So that's what I need to do. All right, well, let's take our message. So when C equals 1, 1 to the 5 is congruent to 1 mod 12, so that one's done. C equals 11, 11 to the 5. Ooh, okay. I'm just going to have to do it. I'm going to just keep having to multiply by 11 and keep figuring out what it is mod 12. As far as I know, that's the quickest way. Has anyone has your lecturer talked through any other ways of dealing with that? No? Okay. This is where it would be useful to have a calculator, because I don't currently have one. That's why it's good to take a calculator to your Maths for IT exam, if you are allowed to calculators, right? Good. See, when I did Discrete Maths 2, which is when I wasn't allowed to have a calculator in the exam. Horrifying. But again, powers, in the same way as multiplication is repeated addition, especially for modular arithmetic, powers for modular arithmetic is just repeated multiplication. So I can just keep multiplying by 11. So let's see. Actually, we can make this way easier. 11 is minus 1 mod 12. And minus 1 is way easier to do powers of than 11. So if you've got a number that's really close to a number like 11 that's really close to the thing that you're doing the mod of, turn it into the minus version and it's easier to do your powers. Because minus 1 to the 5, yes?
Can you go into like how you do that replacement? Like, can you replace any number by an equivalent number? Like, could you replace the 5 by its inverse?
Only allowed to have numbers. So the question for those who are listening online, can you replace this 5 in the power? Is that what you're asking?
Yeah,
do any number?
How does that generally work?
You're only allowed to do numbers that are down here. Powers that doesn't apply to. Because that power is not part of the modular arithmetic. That power is representing 11 times, that power is representing 11 times 11 times 11 times 11, and I could conceivably have 11 to the 216, and that's not the same as this. So actually, I believe the theory goes that the number up here can be replaced with anything mod the number 1 less than this, but only if that, don't do it. So any number that's not in a power, you can replace by whatever is equal to mod whatever. So we might put that in. Note. Any number not in a power by an equivalent number. Is that okay? Does that answer the question? Cool. And that's just interesting because the powers are actually slightly different to the way that the rest of the operations work. So addition, really modular arithmetic is all built on the +1 idea. And so because you can think of multiplication in this context as repeated addition, it's still based on addition. But the repeated multiplication is a different thing. And so it doesn't work quite so neatly, unfortunately. So you have to shy away from powers. And that's one of the reasons why we write powers differently. We write them on a higher level so that we can remember that they don't behave the same as the other numbers down below. Okay, but you can use all your ordinary knowledge of how numbers work as long as it's whole numbers. -1 to an odd power is still -1. Because it's -1 times -1 times -1 times -1 times -1. And there's 5 minuses, and so 4 of them cancel each other out. Not doing well though, because I've got 2 A's in a row, 3 A's in a row. So I might have done something wrong. Has someone got the solutions? Oh, is it mod 21? You're right, it's mod 21. Curses. Sorry about that. It's not mod p minus 1, q minus 1, is it? It's mod n. Thank you. So I'll go and look when I do the recording at when I started to make that mistake, so I can put a note saying, sorry guys, there's a mistake at this time. So back here, oh, you're right, I did it wrong, it's mod n. Sorry about that. All right, let's try that again. Okay, that's cool. And that's going to stuff this, isn't it? Well, it's minus 10. That's not really any better than 11, sadly. If I wanted to replace the 11 with something. I guess it is easier for me to know that what multiplying by 10 is, though. So I suppose I could make it easier on myself. But I might just run with it then. Okay. So we have 11 to the power of 1. Not a multiplication table, it's a power table. Is 11 times by 11 again, which would give me 121, which is congruent to 1. No, it's not. It's congruent to 100 mod 21, which we knew already. I'm just going to have to keep subtracting 21s from it. That's the thing that I find the most useful. If we take 21, that'll give us 100. We could take 4 of those 21s. That would mean taking off congruent to 100. It's congruent to, if we take off 4 of the 21s, that would give me taking off 80, which would be 20, taking off 4, which would give me 16 mod 21. What I do in my calculator is I just press minus 21 equals, and until I get down to something that's less than 21. That's how I do it. And it might even be easier to go down one more step, because that's minus 5. So the third power I times by 11 again, and that'll be minus 55. So I could just keep adding 21 to that. So let's see. If we go up another 21, we'll be at minus 40, minus 34. Up another 21, we'll be at minus 13. And we could figure it out. But anyway, I'll just keep adding 21s. Could someone please add 21 to minus 55 until we get a positive number? I think it's 13.
I'm making an answer of 2.
2? When you do 11 to the 5? I don't know. I'm trying to make it easy on myself. I probably should be just not making it so hard for myself and just timing the 16 by 11 and then subtracting a whole lot of 21s. But I just want to make this number as small as possible, that's all. Just let me do it on my so we have, let's see, we have minus 55. Oh, crap. So plus 21, 8. That's what I get. I just kept adding 21 to what I had on the page. And the fourth power is 8 times 11, which is 88. So just keep timesing your final answer by 11. So I went times by 11, times by 11, times by 11. And I'll take off 21 from that. So let's go back to the computer, to my calculator. We have 88 minus 21, 4. And now times by 11 again, which is 44. And I'll keep taking off 21. 4 minus 1, which is 2. Well done. Good job. And so we can go back to here, which is 2. And so I get that 11 to the 5 is congruent to 2 on 21. So if you're doing it really quickly, you can not necessarily put all of this working in. I don't think they necessarily want to see it, but it helps me to write it down as I go so that I don't lose anything along the way. So let's do that. What number have we got left? The next number is 1. We've already done that. 17. So we need 17 to the 5, not 21. So let's see, power table. for 17 mod 21. So it's 17, which is congruent to minus 4, and then we times by 17. So it's minus 68, and we keep adding 21. We get minus 5, and we times by 17 again, and we'll keep adding 21. So that was 85, by the way. Gives us minus 1, that's kind of nice. So we times by 17 again, and minus 17 would be the same as 4. And then the last one will be 4 times 17, which is 6, which would be congruent to 68, which would be congruent to 5. Because we've already covered that, right? Minus 17 is minus 4. 17 is minus 4, so minus 17 must be plus 4. And then 4 times 17 is 68. It's minus 68 was minus 5, and so that must be 5, and so therefore 17 to 5 is congruent to 5. And we continue on that road, and the last letter C is 11. We've already done that one. Look at them trying to be nice to us. So we have 1, 11, 1, 17, 11 becomes 1, 2, 1, 5, 2. Which is A, B, A. This is bad. That's bad. That doesn't look like it makes any sense. Have I done something wrong then? I mean, really, these two letters have to be the same, the two 11s. What? I feel like I've done it wrong. So, because this doesn't look like a real word to me. But I can't think of any words. I mean, 1 has to become 1. There is no other choice, because 1 to the power of anything is always 1. So it does actually have to be two A's there, and the two, we're pretty sure about 2, because at least 2 people got the same answer. So it must be that my E is wrong. So let me see. Let me try that one again. So let's see. 17. And then times 17. And then times 17. And then times 17. That's what I get.
I got 5 as well.
All right. Apparently the word is a babe. Unless something else is wrong. But 1 has to go to 1. Like mathematically, any power of 1 is 1, right? So even without doing any working, we could know that those two 1s become A's. And if we're sure that the 11 and 5 times 5 is 25, which is 1 mod 12. Like 21 is 3 and 7, and that would give me a 2 and a 6, which is 12. Okay. Sorry, it's unsatisfying, but that's what I've got. So that's what I'm going to run with in my exam. And I would probably say, if I was doing my exam, it's not seen to be a real word. Sorry?
Are you sure you have the right inverse?
I could have that wrong. Unless, just a second, it's only out of 21. Some of those letters might actually be other letters. Like, see everything's mod 21, right? But there's 26 letters. So we've only got 21 numbers to choose from 0 to 20, from 1 to 21, and there's actually 26 letters. So some of these letters might actually be representing something else. The 1 may not be a 1, it may really be a 22, in which case it would be a V. And the B, you see, that's going to be worse, isn't it? Alright, so what if this is still a 1? What if the 2 may not be a 2, it may be a 23, which would be a W. The 5 may not be a 5, it may be a 26, which would be a Z. It's 21, 5 is also 26. A ways? No, I have no idea what's going on, sorry. It seemed like such a good idea. Has anyone got solutions for this? Did they sell solutions to this?
They did, but I didn't.
Sorry?
They do, but I don't.
Okay.
They're still in a huge box, right?
Yeah.
I think all this solutions managed to get right.
No, I'm sorry. I'm now stumped. But that would have been my normal instinct to say, well, there's only 21 letters to choose from, so there's 26 letters to choose from. But because it's mod 21, all your letters might be two different numbers out of 26. So. Yeah, because if we had the number, say, if we had the letter, say, V, it's 22, which would become a 1, and then when you did it mod 21, and so, but I can't make that work. A ways work. No, sorry, no idea. I really apologise for that. If I could figure out who was lecturing it in 2011, I could ask them. But I don't know that answer at this time. Actually, that person has left, I think, so we will never know. But we've done everything correctly in terms of the modular arithmetic. Okay. I think that might do it, unless anyone has more questions about RSA or cryptography in general. I can move on to something else, but does anyone have any more questions about that? No? Okay, cool. I might leave it at that. The hard bit is that modular arithmetic, and I do find that being able to think of powers as repeatedly multiplying things, and addition as multiplication as repeatedly adding things, are three useful strategies, two useful strategies, and also replacing any number at any point in your calculation with something else that it's equivalent to is not such a bad plan. And so here, that minus 1, leaving it as a minus 1 makes my next multiplication easier. So I'm just going to point out that I just keep timesing by 17 here. All right. Sorry about that, that's unedifying. I mean, we do know that whatever happens, these two are the same letter, or at least representing the same letter, and these two are the same letter. And we knew it was one word, but I feel unedified. If I find out when I... Yes?
Just like for a further example, would you be able to do the Euclidean division algorithm to find an inverse?
Certainly, I can do the Euclidean algorithm to find an inverse. It might be a good idea to just